Today, our second keynote, Subhash Guddard from Google, he briefly touched upon Google's cloud-native Postgres offering in AlloyDB. And to talk more about the same, we have his colleagues Paresh Rathod and Sriram Melkote from Google. Please welcome them.
Hello. All right, good afternoon. I still don't hear you. Good afternoon. One more time. Good afternoon. Okay, I guess the lunch is settling now. Thank you very much, Pinas, for the warm welcome. I've spent my time, bit of background about myself, and then Sriram, you can. I've spent a lot of my time in the industry in the closed source databases such as Sybase, IBM, Informix, and SAP. So my journey into Postgres ecosystem is fairly young. And very happy to see the Postgres enthusiast of the ecosystem actually attending this conference. Today what we're going to do is introduce AlloyDB PostgreSQL to us. Before I kind of go ahead, Sriram, if you would like to introduce yourself.
Sure. So I'm Sriram Melkote, and I work in the AlloyDB Bangalore team. I have worked with databases both as a user as well as a developer of databases. And my interests are Golang, programming, hardware, and of course I have two kids who I spend a lot of time with. It's been a very interesting journey, and I'm looking forward to presenting it today.
Wonderful, thank you. All right, so connecting back to the morning keynote by Subhash about what we are doing in Postgres ecosystem in the context of the Google Cloud. Today's focus area will be AlloyDB, but I'll walk you through a bit of the holistic context of it, and Sriram can spend more time on the details of AlloyDB part. So what we are hearing from our customers primarily is that, hey, building applications in the context of the cloud, at the heart of it is the operational databases. And the operational databases, what we are looking at from the cloud journey is agility, cost, ease of use, and the differentiated capabilities. We anticipate that a lot of the on-premise databases that exist today are going to migrate to the cloud pretty soon. The other thing what we hear from our customer is that at the heart of it, Postgres is very popular database of the choice. Not only for the Postgres existing customer base, but also for the digital native application developers, as well as the customers, enterprise customers who are using today commercial databases. And we are seeing a great momentum in the favor of Postgres. And it's pretty evident that Postgres comes with a lot of qualities that are so important in the cloud. Portability, its ease of use, it's cost effective, extensive architecture. It's a proven technology with mission-critical applications that are already running across many different industries. And last but not the least, actually, the strong community that we have here, which are gathered today and beyond. In Google Cloud, we have a wide variety of databases, actually, that serves different type of workloads. So what you see on the slide here is that on the extreme left, the in-memory solutions for memory store for Redis, to relational databases such as Cloud SQL. Now in the Cloud SQL, actually, we provide Postgres as a service, we provide MySQL as a service, we provide SQL Server as a service. Also the new database that we just launched is AlloyDB, which is again a Postgres-based service, and the Spanner, which is truly global database. Also, we also have the non-relational databases such as Firestore and Bigtable. All of these database services underneath are powered by the Google infrastructure and are the same infrastructure that many applications that we have been using in the context of Google on a daily basis. For the Postgres ecosystem in the Google Cloud umbrella, there are three services actually that we primarily are focusing on. One is the Cloud SQL for Postgres. The second is AlloyDB, and third is the Spanner. We heard in the morning talk about each one of that. We're going to focus more on AlloyDB today. Before we kind of get into the AlloyDB, one of the compelling factor of Cloud SQL is that it supports multiple Postgres versions, major, minor versions, comes with a lot of flags and extension supports, trusted reliability, 99.95 availability aspects of it, powered by the Google security. And the other very important part actually as an application developer is that it's very well integrated with the rest of the Google ecosystem. So for example, for analytical purposes, Cloud SQL is very well integrated with BigQuery, Looker, works on GKE and Cloud Run. Also comes with an kind of enterprise-grade observability. AlloyDB, so we have been working on AlloyDB for past few years. And we just recently launched AlloyDB in December 2022. It's freshly out of the gate. There's a lot of interest shown by our customers. At the heart of AlloyDB, it's a goodness of mixture of things actually. And Subhash mentioned that Alloy is nothing but a mixture of metal for better metal. So here what we see is we bring the goodness of Postgres, which is great extensive architecture. And Postgres and AlloyDB is fully compatible with Postgres. And we kind of blend that with Google Cloud native technologies such as disaggregated compute and storage, intelligent caching, AI, ML powered, ease of use of management, etc. The focus area that you have focused on while building AlloyDB is scale. Scale in multiple dimensions. How do we scale transactional workloads? How do we scale the analytical workload? How do we disaggregate compute and storage such that you could actually scale the compute separately, scale the storage separately? In context of Alloy, scaling the storage is automatic actually. So if you drop a table, actually your storage is lesser size. If you create a table, the storage is higher size, and you pay as much as you use. The other aspect is performance. Again, two dimensions here. Performance, typically operational database, it's transactional workload. But they are also used for certain read reporting applications, certain analytical applications, maybe not the most advanced analytical applications. So performance in the context of both the transactional and analytical workload, you could perform that on the single engine, which is typically what we have been doing is to say that, okay, take the data from the operational database, do an ETL to an analytical engine, and perform the analytics. On AlloyDB case, actually, we have the same engine, same schema. The data movement actually from your primary node to the read nodes happen on its own. And you can actually scale your read applications by adding multiple read nodes. Availability has been a very important aspect for us. So we kind of move from Cloud SQL 99.5 availability to 99.99 availability. We also have focused on a lot of ease of management. For example, out-of-disk errors, out-of-memory errors, with a lot of AML techniques actually. There's an interesting demo that you will also see using the Vertex AI service, how we have been able to augment the transaction using that part. Alloy also comes with a real-time observability such that it enables the developers to go from detect to diagnose journey using the observability around it. While Alloy is fully compatible, it's fully compatible with Postgres 14, which means that if you have an existing application of Postgres, you can use as is without any change, and it works with Alloy. It comes with a large number of flags and extension supports today. With that, I'll have Sriram share a little bit more about the inside, deeper details and the design and architecture of AlloyDB.
Sure. Thank you, Paresh. So let me start a timer so I don't go over. Okay. So how many of you write code? Okay. So you will all know when I say you start writing code, it looks great, and then you take it to production, you add some bug fixes, and 4 years later, more bug fixes, some hacks, it's beginning to look a little ugly. Another 4 more years, now what should take 1 week now takes 1 month to get done, and then that increases exponentially. And then you have 10-year-old software which no one can understand, and then you rewrite it. This is a very common thing. I'm sure you have seen this in your own professional lives. And what is remarkable to me about Postgres is how it has not followed this path. The fact that everything I'm going to talk about today, AlloyDB, is done on top of Postgres using Postgres extensibility mechanisms is remarkable. This is an example of a truly well-engineered software, and there is something to be said about Postgres for being so vibrant even today, despite all the iterations it has gone through. Let's take a look. So as you know, the computer as it existed when Postgres was built was a CPU and a disk and some memory. Now fast forward many years, we have cloud, and one of the most important parts of cloud is that these are all virtual now. So you no longer have a PC, and your storage is basically a block store sitting somewhere. It's really a service. So being able to disaggregate compute and storage is a very important thing that we can do in cloud, and this is one of the key things that AlloyDB leverages. So it's a modern architecture, and we have the ability to offload I/O to a horizontally scalable storage subsystem, and this gives us predictability in costs. So with AlloyDB, if you create a table, you pay for it, and you drop a table, you no longer pay for it. And the size of the disk is essentially unlimited. So by being able to separate compute and storage, we can gain new abilities from the same software that didn't exist before. So if we take a little bit deeper look, you will see that we have a primary. So we have a primary, which is where the Postgres kernel is running. And then we have a failover, which is a replica that can run. And then we can have one or more read replicas running in their own pools. And as with some of the modern databases, we only send the log from the primary onto a storage subsystem. So we never send the blocks to the storage. And because we send only the log, we are able to have very high throughput. And these logs go to a sharded storage subsystem, and this can scale up and down on demand. So as you know, with databases, storage is often the bottleneck. And by making storage a scalable layer, and by using logs to communicate from the query processing engine to the storage engine, we can effectively take away this bottleneck and make it into a scalability point of the system. The read replicas too have access to this joint storage, and so they can get blocks from the logs that have been created. So the log is sent, the log process create the block images that goes into Google's Colossus. It's a Google-wide storage system which is highly scalable. And these manufacture and store the blocks, which is available for any node to use. So we get scalability even though we are using a single primary node. The other nice part about it is the compute is essentially a throwaway part. We can create more, we can remove more. If we want to do failover, we can switch from one node to another. That's because the state of the system is now captured in our storage, and it's sharded and scalable. So we can add more nodes, we can take away nodes and do it dynamically. And our failovers leverage this as well. So I think the other interesting thing that we have done in AlloyDB is to build a columnar engine. As you know, as Paresh said, the theme of nowadays is you don't want an analytical system and a transactional system to be two different things. You don't want to be the person moving data between the two. So you want to have one system where you can run both transactional workload as well as the analytical workload. And as you would know, analytical workloads often prefer a column major format. So we decided let's build an extension on top of Postgres that's going to build a column major format. Now obviously you don't want to store all your data because that's going to be inefficient, and it's also not compatible with Postgres architecture, which really looks at it as a row major format. So we took some subsection of your data and we put it in a column major format, and we hold it in memory and our disk and other storage mechanisms. What this lets us do is to take a query that scans a lot of rows and be able to use vectorized instructions to run them efficiently, because the columns are all contiguous, and you can do aggregation operations using hardware instructions. You can operate at a much faster rate and pulling in much fewer bytes of I/O than you could do in a row major format. Now, this is all nice and nice on the paper and to talk about, but to actually do it is very hard, because many a times a lot of database users don't really know what queries they generate, because they use an application. You use an application like a CRM application, you install it under database. So the query, even though you might understand it, you may know how to optimize it, it's still a black box because you didn't write the query. And very few database administrators want to go mess with the queries because it's being generated by an application. And even if you optimize one version, an upgrade may come along that may change the schema significantly, and what you had done in the previous version now may become an impediment. So you really want the system to manage it, and that's what we strive for in AlloyDB. As you can see in the picture, we have our columnar format. We do things like min-max. We have a Bloom filter to see if something is present or absent. We have the ability to filter, and then we can do pruning. But all this happens in a set of columns which we determine at runtime using the queries that you are running. So your queries start by running against the Postgres row store, and our machine learning models look at them over a period of time and say this query can benefit by using a columnar format. We then assemble the data in columnar format, and once the columnar units are ready, the queries now start executing against the columnar unit. And this changes over time. So if you upgrade your database, as a user, you do not have to care about this. This happens entirely in the background, and this is how we are able to accelerate analytical queries. So here is another view of it. Now, one key point, if you are a Postgres fan, is that you will say that why don't you just give the memory to buffer cache? Why do you want to hold columns in this columnar format? And it's always a trade-off. Given X amount of RAM, what portion of it you allocated to the buffer cache, and what portion you allocated to holding columns or other data to accelerate queries? There is no right answer, and this is one more place where we use ML. We look at the queries, we look at the workload, and we use that to determine how much is the optimal split between the columnar units and buffer cache. We also use tiered storage. So because our compute nodes don't hold the final state, we can treat our compute nodes as cache, and we have different types of technologies. Storage is a rapidly evolving area. We can use the DRAM that's available, we can use SSDs that's available, and any number of tiered storage we can utilize to accelerate it. The ultimate source of truth is in our sharded storage, and so everything in between is a caching layer. So we use ML to manage it, and that essentially frees up the database administrators from having to figure out these magic parameters that work well and need to be tuned. It's a part of a journey. There's a lot of work to be done, and I think with all the ML and all the AI talk happening, it's a very interesting area to be, and this will definitely evolve as we go forward. So I can show a quick demo of AI at work. So while AlloyDB uses AI to optimize itself, we have also built an extension that allows customers to use AI using your own queries. Again, this is done using the Postgres extension mechanism, which is quite remarkable because it makes it very easy to utilize our other offerings such as Vertex AI. So today, let's look at an example. Let's say somebody is running a shopping cart, and many a time you have some elements where some items that you might have negotiated a good price for. You want to sell it to final users. You don't want a wholesaler to come buy up your entire stock. Or you might have a loss leader item. You want to make sure that every person purchasing it is doing so in small quantities. And these are difficult patterns to really find using fixed rules. And this is one place ML does very well. It looks a lot of data like your own purchase history, or how long you have been a customer, or what is the profile of customers purchasing from the website today. And you can train a ML model that's going to decide if this transaction is allowable or not. And you can do this across our database offerings, just like you can do it this way in AlloyDB, you can do so in Spanner. So we have the consistency between our offerings. And for Postgres, this is an extension, so it does not come and interfere with Postgres compatibility in any way. So let's take a look at an example that I'll run through today. I have a demo recorded, but in today's demo, we are going to look at a credit card transaction. So a credit card transaction gets inserted into your database. We are going to send it across to a machine learning model that we created, and then we'll use the model to decide if it is a fraudulent transaction or not. And we can do this using standard SQL, which is what I hope to show now. Before that, let me show you how to set up AlloyDB. It's very simple, one screen, and you give the name of the cluster, and then you pick the machine type that you want to use, and then you pick the network you want to connect it to, and then you click create, and you have AlloyDB cluster running. So do try it out. It's a very easy start, and it's a good way to use Postgres. So once we have AlloyDB cluster running, let's see what it involves. So here we want to invoke Vertex AI predictions. I see Vinay is there. Thank you so much for recording this, Vinay. I appreciate it. So today we are going to use our ML predict extensions to do the call out. So the first thing we are going to do is create a cluster, and we are going to look at the cluster name, and we will want the project ID of it. So the first thing is you have an ML model deployed, and you want to provide access to it. You want to secure it, and you want to first provide the security role grant. So you take your project number in which you have hosted the Vertex AI endpoint, and then you choose the endpoint, and you are going to provide a role grant to it. What we are going to do in this is to essentially tell the model that AlloyDB is authorized to query this particular ML model which has been deployed. And you see this in progress. So we pick the project name, and we say grant permission to it. And the permission we are granting is the Vertex AI user endpoint. And once you do this, you have given your database permission to send queries to your ML model which is hosted in Vertex AI. So here is how it looks. You can also have prepackaged grants. That's the box you see on top, which is going to let you see other things that might come out of the box. Now once this is done, the fraud detection endpoint is created, and you have authorized AlloyDB to use it. Then we can switch to SQL, and we can start utilizing it. So let's take a look at that. So here is an example of a JSON request that the model expects, and this is what AlloyDB is going to generate. And you can see that it's deployed in the US Central 1 region. We'll see how performance works. Since this is a call out between two products, there is a performance aspect which you will see today as well. So here we run the PG client, and we get our dear prompt, and here is the schema that we want to utilize. Let's create a table, and then we can load some data using a CSV file. This is a well-known fraud data set. This is a set of credit card transactions. We will do the load, and here is how the data looks like. You will see that the data is anonymized. This is because this is real data, and for privacy reasons the data set is anonymized. But it doesn't matter for our model because we are essentially looking at the numbers. Now once that's done, we will issue the select statement. So the fraud detection data set is done, and we are going to create an extension, Google ML integration. That's the extension that we have created. Once you do this, you get the ML predict function that you see here, ML predict row. The first parameter you see is the endpoint. The endpoint essentially gives the number of the Vertex AI endpoint that you want to talk. It's saying query this model. The next parameter you see is that we do JSON build object and we send instances, and we use our Postgres function row to JSON. This takes the current row the query is processing and make a JSON object out of it. And then we finally send it to the endpoint. Now the result, you get a field called predictions, which we are going to select as fraud score. The key thing I want to call out here is this all standard SQL. The only new thing that we have introduced is ML predict row. And when we run this, you will see how the data set looks like. We are going to run it on 500 rows, and you will see that this is the results. There are two classes of results predictions are provided. Class 0 is the probability that it's a genuine transaction. Class 1 is probability that it's a fraudulent transaction. You will see that the first row has a 99% chance of being genuine. And likewise, you will see that it has a very small chance of being fraudulent. So your model is telling you this is a genuine transaction. If you look at the second row, you see the reverse. You see that there's a 10% chance that it's real, and correspondingly 90% chance that it's fraudulent. So in the course of a single select or insert statement, we can effectively do the ML predictions. You see it took 14 seconds. It's quite a bit of time, and you may not want to spend so much time on a single query. Most of the time, if you were to analyze, is going into doing the calls and getting the results back. And the usual solution to something taking time from latency is to do batching. Again, we'll use standard Postgres to do the batching. We do a group by here and on a random integer. Essentially, that group by is going to create 5 or 6 batches of data. And we are going to use some of the functions such as JSON build object and JSON ag. For those of you who know, JSON ag will take your batch and make a single JSON object out of it. Then we are going to send it to ML predict row. And then we'll use unnest and JSON array elements to unpack the results to get the corresponding results out. And you see it's much faster, it took less than a second. And this is again magic of Postgres at work. All we provided was the ML predict function, and Postgres is taking care of providing the ability to do batching and do the call out. So this is just some of the demonstration of how we use ML ourselves, as well as offer it to customers to be able to utilize it. So do give AlloyDB a try. You may find it interesting.
Thank you. Wow, that was working. Right. The other interesting topic with AlloyDB is the AlloyDB observability. We call it as an AlloyDB Insights. Now, Sriram talked about that there are many moving parts in the system. There is a primary node. There is different storage tiers. There are multiple read replicas. One of the important part is to know that, hey, how the system is behaving. How do I know what are my top queries? How do I know what are the connections to the system? How do I know how much is the transactional workload? What are the commits? What are the rollbacks in the system, et cetera, right? So it's very important to have the insights while you build the system, but to provide ability to have the insight into what's happening in the system. So AlloyDB Query Insight is a three-dimensional work. So one of that you can see is that first is to say that, hey, what's happening to my query workload? What are my top queries? What are the issues with my top queries? Are there log contentions? Are there planner issues, et cetera, et cetera? The second is at the system level to understand, for example, hey, what is happening? We talked about a lot of columnar engine. How is the columnar engine being utilized? What's the memory that it occupies? So there's a lot of information at the system level. And third, which is to say that, hey, could I have assistants on the top of it? Could I have some advisors on top of it? So we built some advisors called index advisors. Again, it looks at the system, it looks at the workload, applies the ML techniques, and figures out that certain queries on certain tables will benefit by having indexes, and would recommend you to have the indexes on those tables. So that's one form of the advisors. What we are trying to do is, there's a lot of goodness of advisors that we have built over the period of time on Cloud SQL Postgres, and we are trying to bring them to the Alloy world actually, such as, let's say, cost optimization advisors, etc. There's another view actually. What you see here is that a snapshot of looking at the system to say that, hey, there are some queries which are actually having peak load. What are the issues with the queries? You could look at a query plan. A plan visualizer would enable you to go from detecting the problem to be able to identify some diagnosis around it. One of the important part of the query insight is that all of the system is serverless, which is you need not deploy anything. You did not provision anything. AlloyDB by default collects this rich telemetry, whether it's matrices, traces, query plans, etc. All of that is with a very minimal overhead to the entire system. At the same time, it stores and retains it today currently for about 7 days. All of the data is securely stored per customer project basis. And what we intend to do with that is to be able to provide in future longer retentions on the top of it, longer fine-grained analysis on the top of it. Like, for example, most of us from the Postgres system would be aware of wait event analysis. So how do you take the wait event analysis and wait events and couple it with what's happening in the system to get much more fine-grained analysis on the top of it? The other interesting part is, more often than not, actually, the performance is being looked at from the query-centric point of view. Like, hey, these are the number of queries that are running in the system. These are the top queries, and they have some issues. But the queries may originate to a single database, actually, from multiple applications. And you may want to correlate between, hey, which query is coming from which application? Is it coming from a payment application? Is it from a banking application? Yes. Yes, yes. So, for example, you deploy an AlloyDB instance. By default, the capturing of this rich telemetry and then the visualization on the top of it is done by default. So you need not deploy an additional service to capture the telemetry, to monitor it, and other services on the top of it. Yes, yes. That's true. What we have done a lot of internal benchmarking actually to ensure that the queries and matrices that we capture is capturing with certain intelligent sampling such that the performance overhead remains beyond a certain bound. Typically, you will see from our internal benchmarking, what we have learned is that it remains within the 5% bound actually in the system. But if you tend to capture everything, certainly we run into the issues that you mentioned for sure. Yes, yes. So there are other strategies which are being built out. So for example, when you're doing any form of sampling, you're building sampling based on certain strategies. Let's say execution times, etc., right? So what we are trying to do additionally is to provide users some control to be able to provide the strategies and influence the sampling algorithms to be able to sample the things of your interest. Again, by remaining within the bounds of the performance overhead. All right. So how do you connect the applications and how do you connect the databases and the queries running in the databases? So what we enable users is to be able to provide tags to the queries. So you can say this query is coming from a financial application, this query is coming from an HR applications, etc. And then you have a visualizer which kind of says that, hey, what are the top database workload that is happening at this point of time in my system from which application? So you can kind of focus from application and then go to the query as well. The other interesting part is that all of these insights is also accessible through various open APIs. So it's an open standard, open telemetry APIs. Also, Google's other services such as cloud monitoring and cloud trace, they also have APIs with which you can actually not only take the data coming from the database, but maybe if your application is using cloud monitoring, then you can combine the insights that come from multiple systems and create your own customized dashboards. You can create alerts. You can create notifications. Those notifications potentially can go to your SMS or pager or an email, et cetera, et cetera. So creating the insights, providing the open APIs enables not only the pre-built dashboards that we provide, but in addition to be a capability to build your own dashboarding, build your own logic and notifications and alerts, etc. In addition, the other dimension is migration. So we all know that migrations are very challenging. There is a service called DMS service which is provided that migrates the Postgres workload to AlloyDB. This is fairly new, actually, so I would also encourage to try this out. And additionally, on the migration topic, we know that some of the migrations are easier, some are very, very challenging. To be able to work on those challenging migration topics, we also have a comprehensive database migration program where the experts can help migration of the workload from the heterogeneous system into the AlloyDB. Last but not the least, actually, to sum it up, a lot of things that Sriram spoke about and something that I spoke about. AlloyDB, why do you want to choose AlloyDB? Certainly at the heart of it, it's all powered by Postgres, right? It's an amazing architecture, extensible architecture that you could build so many different techniques around that. One, it is compatible to Postgres 14 today. As newer versions of Postgres starts coming in, actually, we will be employing a strategy to have a fast follow of AlloyDB compatibility to that particular version. Performance, both transactional and analytical workload on the same engine, getting rid of the ETL, that's a major advantage. Being able to scale the compute and storage separately. The storage is actually scaled automatically, so it's on-demand automatic scaling. It's reliable, scalable, highly available. You can create multiple read nodes. Each read node can have multiple computes, and overall summing up to about 1,000 compute on the read side. Automation, Sriram touched upon some of the aspects of automation. And on the top of it, a lot of sophisticated AI/ML capabilities, the demo that we saw of the augmented transactions. So there's lots of cool things that are being built around the Postgres heart of it, and that's what the AlloyDB is all about, bringing the goodness of many different dimensions together in that sense. With that, I would like to conclude today's session and open for questions.
Yeah, the mixed workload, what you said. So do I get a chance to choose which can go into row based on which can go to column based? I mean, at what level? Table levels, or how can I do that?
The approach we take is we don't want users to have to make that choice because it's always complex. If some of your queries are hitting only 100 rows, it's very likely index scan is going to be faster. But if it is hitting 10 million rows, you probably want to do a columnar scan. So our approach in AlloyDB is to let the system make the decision. So you just use it like a Postgres database, and behind the scenes we'll decide that your queries would benefit by having this column stored in a column major format, and we will build it, and once the columnar units are ready and built, the queries will switch to using the columnar unit. So in general, you shouldn't have to make that decision, the system would do it for you. For the niche case where you do want to have control over that, we have flags that will provide you control. You can override the system and say, I want this column always to be also materialized in column format. So both are possible, but we encourage people to let the system deal with the columnarization.
Another question about the serverless stuff is, like, these days we are hearing a lot that it adds the nodes or it adds the more power as the usage required. So that point is not completely clear to me, like say when the query is performing at X speed, and how and when such serverless architectures decide that now we should add more power to it, like node. Is it something like that?
I can take a stab at it first, and maybe you may chime in. So the serverless, the point of serverless was in the context of the database observability topic, right? But for the Alloy itself, you kind of pre-choose actually how much amount of compute that you need on your primary, how many read pools do you need actually.
Okay.
You can scale those over the period of time, but you start with a configuration. So in
Okay.
true sense, it's not a serverless in that concept,
Okay.
right? But there are other systems that you're building around it. For example, the database migration service or the observability service. You need not do additional provisioning for those actually. Those become serverless for your particular cluster of AlloyDB.
Okay. So this is partially serverless.
Yeah,
sort of.
for certain capabilities, yes.
And I want to add, we make it easy to add and remove servers. So you can add a read pull node and you can remove read pull node without downtime. And we can do that because our storage is separate from the compute. So you can add compute as you need it and remove it when you don't need, without taking downtime or without having to worry about prefetching data and loading it. So while, as Paresh said, you provision the size of the cluster, we make it easy for you to scale it up and down according to your needs.
Okay. Thank you.
Sure.
Yeah, I have a question, like, is there any performance impact on the DML sensitive load, like when you write to your columnar format as well, along with the Postgres storage, right?
I want to add to that question. So, for the table on which you want to run real-time analytics, that means for the tables on which you want to run real-time analytics, that means you keep the data in both columnar and row store. So do you see any OLTP performance impact, especially on the single thread?
Yeah, I think as you point out, performance is always a trade-off. There are times when you take the effort of materializing it into column major format. It may turn out that your queries don't improve that much, but you slow down your writes. But there are other workloads where having the column major format will give you a 100x improvement in speed. We have examples of those queries and benchmark against it. It's very tricky, and that's the reason why we are building ML models to make the decision for you. So for queries where having the column major format will benefit, we build it. We build it asynchronously because we see that column major formats are often useful when there's a lot of data that changes less frequently. So packing it into column major format gives you the ability to scan large amounts of data in small amounts of time. For those queries, we build it. For queries which will benefit from using the transactional semantics like the row store and indexes, those continue to work. So there is no fixed answer. We let the ML models decide it. And ML models are something that we continually tune. Things like planner weights and when planner should choose this versus the other query is something we continuously tune from our end. But as a user, we don't want you to think about it. We just want your queries to run faster. If they benefit from column major format, we want to materialize it for you behind the scene.
If I may add, and Subhash, maybe if you add after that actually, right? See, one of the things is we don't write it in both format. Okay? So the data is written in only in the row format. It's actually you transform in the columnar format in the memory based on the need actually in that sense. So that's a subtle difference.
That's asynchronous.
Yes.
Yeah, that was one of the points I was going to make as well. The columnar store is not in the path of the commit, right? It's only the row store, that's one. Second is, typically if you did not have the column store and if you wanted to build analytical queries, what would you do? You'd build indexes. Right? And indexes, obviously, we know has a maintenance cost associated with that. The moment you go to a column store, you can potentially drop multiple indexes for those analytical queries, which also make your inserts and updates faster because that index maintenance is not needed anymore. So that's the other way of it.
How does, I mean, in general, when you have a issue with a SQL weak slope, you look at explain and you try to work around, okay, how does it do it? How does that show up on an explain that it's currently working with this path, or is it in a columnar which is in memory or whatever? I mean, how does that show up on someone who's using an SQL and suddenly it's slow? What's the answer?
Sure. So from a user point of view, the primary place you will see it is when you do an explain. You will see that what might have been a sequential scan or an index only scan will now show as a parallelized columnar scan. So that's the main indication that it's now using the columnar format. But the query semantics and consistency guarantees, all of them remain the same.
Hi, you mentioned like there's an ML engine which is constantly observing our query patterns and the data. So I just have a query about the security of the data. So if an ML engine is constantly observing the data and the pattern, how are you ensuring that okay, this data is very private to my use case only and it's not, getting lost anywhere?
Yeah, I mean, the data doesn't go out of the VM of the cluster that you have. That's the first primary part of it, that anything that happens in your cluster remains in your cluster.
Yeah, but there is something, outside of my control, right, who is observing my data. What if this is PCI data, PII data, somebody outside of my system is observing my data? How secure is that?
Yeah, one of the things that we do is that we do a lot of anonymization actually before the ML also starts to take a look at that. So that is one thing that we carefully look at it. And also the data doesn't leave the VM at all. So these are the two aspects that we kind of do to make sure that the data is secured.
Yeah. And okay. I can add in since I'm looking at PCI and HIPAA compliance. So I think it's a topic that we spend a lot of time and energy on because our bigger customers have very strict requirements around where the data is, data at rest, data at motion. They have policies, and as a product we have to comply with those policies. So we build it into the product, and any of the ML optimizations that we do with the query does not leave the boundary of your project. So we have CMake, so you can have your data encrypted, and so Google is not even able to decrypt it even if we have access to the raw storage. So we strictly follow the privacy and security guidelines, and it's in fact one of the strong points of AlloyDB that we can serve enterprise workloads that require data residency, access transparency. We can comply with HIPAA, PCI and other industry standards. And this is one of the key value additions that we have brought in AlloyDB. But absolutely, we make sure that data resides within the project, encrypted using the keys that are provided by the customer. And where we take it out for purposes such as insights and monitoring, it is explicitly anonymized and done only to the policies that the customer defines. It's quite hard and tricky because you have data centers, you have sharding. But this is where we bring the value addition being a managed offering.
One last question before we break for tea.
Hello, hi. So does this replicate globally to other regions of the cluster? For example, West 1, West 2, East 1, East 2, the read replicas.
So we have two different kinds of replications. You have the primary, and you can set up read pools. You can think of this as scaling the database. The read pools are in the same region as where the primary is. That's your primary location. We also have another feature called cross-region replication. That's currently in preview and should be going GA in the very near future, which will let you replicate data across zones as well. And customers are interested in it typically for data resiliency, for disaster recovery. We have both flavors of replication.
Okay, so it's still not GA. So because my concern was in other cloud native databases, what you have seen is globally read replicas which are in other regions usually lag behind and they need to restart to catch up with the primary. So since it's not GA, we are not actually sure whether this is the case with AlloyDB, right? Or you have seen this?
Yes. One thing to keep in mind is because we disaggregate compute and storage, we can access our blocks wherever the blocks are accessible. So we have a choice of storages, some of which are local, some of which are distributed. So we are not necessarily bound the way a traditional replication would work, where it has to wait for the stream to reach. But we do measure our read replica lag times. It's one of our key performance indicators, and we do intend to keep it as minimal as possible. Of course, physics always wins over speed of light is only this fast. So when we do cross-region replication, there is going to be a latency, but we try our very best to keep it as low as we can. This is one more place where being with a provider like Google is helpful, because a lot of times you have software, but some of these latencies really depend on the network. Google owns a lot of fiber, and Google has some of the most optimized networks historically, because Google has been such a large content driver. So when you use AlloyDB and use cross-region replication, you gain the benefit of these products. You can use Cloud Interconnect, which is a premium service, which will help you bring down latencies. So we optimize not only at the software layer, but also we offer some of the lowest latency networks you can find in the commercial industry.
We'll have a quick break for 30 minutes for tea. I'm sure Paresh and Sriram will be available, so you guys can take your questions with them after that. Thank you.
Thank you. And we also have a booth outside. We also have a booth outside, so we'll be happy to take the questions there as well.
Absolutely. Thank you, everyone.